artificial intelligence emphasizing deep learning. So artificial intelligence started in the 50s and 60s. The thought initially was that it was going to be easy. So for example, there's this thing, the Summer Vision Project at the Artificial Intelligence Group at MIT, middle of 66. The Summer Vision Project is an attempt to use our summer workers effectively, I think we're undergraduates, in construction of a significant part of a visual system, pattern recognition. And they thought, yeah, summer, we can do this. Well, it turned out that the things that are easy for humans to do are very difficult for computers to do. Humans, at a very early age, learned to discriminate between different kinds of animals, for example. It turned out to be very hard to get computers to do that. So everyday tasks that we consider blindingly obvious has been very difficult for computers. Recently, in the last decade, and especially the last 5 years, the ability of computers to do these things has improved tremendously because it turned out that you can train computers with vast amounts of data if the computers can learn. And this has now been very effective for machine translation, face recognition, and many other things, many of which you've probably heard about or even experienced if you've used, for example, Google Translate. Does it also work, face recognition, for Galaxies? That's one of the things we're trying to find out. Here are examples of the kind of things that the computer classification can do. It can classify different kinds of flowers, it can generalize, and it can even make reasonable mistakes. That's the local mascot of UC Santa Cruz, the banana slug, and it's reasonable that it would mistake that for a snake. Now, from the beginning, there was a controversy between two different approaches to artificial intelligence. One approach was basically mimicking the way the nervous system works. So the way an axon works is that it has lots and lots of inputs, up to 1,000 or so inputs, which are mediated by the synapses. And then the axon decides whether or not to fire. And if it fires, it's a step function. It either does or it doesn't. And then it connects to more nerve cells, and that's how the nervous system works. So Frank Rosenblatt and others decided that that was the way to build computers that could solve these kinds of problems. But the general view in the community, represented by Marvin Minsky, one of the founders of artificial intelligence and one of the first directors of the Artificial Intelligence Lab at MIT, was no, that's not what you do. What you do is you instruct. You give lots and lots of detailed instructions, like in an engineering program, describing the features, for example, of cats or dogs or whatever, and that's how you're going to do recognition. And that was, I think, sort of the general view of how it should work until about 5 years ago, 10 years ago maybe. So Rosenblatt and Minsky in particular argued about this for a long time. During the 1960s, neural net researchers, that's the Rosenblatt approach, tried various methods for changing the adjustable weights in the parameters. And inventive schemes were tried for making weight changes, but none ever seemed to work out, according to Niels Nielsen, who wrote this very nice history of the field, which you can download. The problem was solved in the mid-80s by backpropagation, backprop for short, invented by Geoffrey Hinton and others. And the basic idea is to calculate basically a steepest descent method to decide how to change all the parameters in multiple layers consistently to steadily improve the way the system predicts the outcomes and thereby does the correct classifications. So nowadays, these systems can classify many, many different things. 1.2 million images in this standard database, no problem. And they classify them very accurately. But to do that, they need enormously large systems. So this is an example of a competition that's taking place every year. And up until 2012, it was always won by the old-fashioned approach, where many, many different features were identified and then used to describe the various systems. And in 2012, Hinton and his collaborators had a deep convolutional neural network, which we call deep learning, and that won. And every year since then, all the winners have been of that type. And now that's completely swept the field. This was the paper of the people who won. They had 60 million parameters, 650,000 neurons, like the neuron that I described at first, except they don't use a step function output. It's calibrated. And they're much, much better. Their error rate was 15% compared to 26% by the second best entry. So they just completely swept away everybody else. This is a description of how the thing works. So these are the perceptons, and then there's always pooling layers that connect the different things that are found in different parts of the image and so forth. So the ideas have been available certainly since the 80s. What took so long? And the answer is that these things are very complicated. They require powerful computers, and in order to describe millions of different images, they have to have millions of parameters. So it's been the existence of very powerful computers, especially graphic processor units and better code, that's made this possible. How is this relevant for galaxies? Well, the first example I know was Sander Dieleman, who was then a graduate student at the University of Guelph in Belgium, won the Kaggle competition. That's a competition for machine learning. In 2014, the game was that there's this project that you probably all know about called Galaxy Zoo. This was Galaxy Zoo 2. So nearly 1 million people classified nearby Sloan galaxy images, and there were 37 different possible outcomes if you followed the decision tree. First they classify spheroid or disk, and then if it's spheroid, they answer various questions. If it's this, they answer various questions. And so there's 37 different possible outcomes, and Dieleman predicted the outcomes more than twice as much better than the next nearest competitor. So he totally swept the field with a deep learning type program. So this was his deep learning program, described in this sort of plot that shows how you combine different size regions and you pool to connect layers. So fine, they're able to reproduce the human classification extremely accurately of these galaxies. What about high redshift galaxies, which are much harder to describe? So there's a set of about 8,000 of the CANDLES galaxies that were classified by CANDLES astronomers, about 65 astronomers, each one classified independently by at least 3. And so Mark Huerta's company, who's here, why don't you raise your hand, Mark? So he got Dieleman's code, and he modified it only slightly and used it to classify. He trained it using the 8,000 galaxies that had been classified by CANDLES, and then he showed that it could classify galaxies as well as any CANDLES astronomer, and then he used it to classify all the CANDLES galaxies, and he did it very fast. It only took, I think it took an hour to classify 1,000 galaxies. So it was possible then to classify all the CANDLES galaxies, and having then done that and published that, Mark then used the classification of all the CANDLES galaxies to describe the morphological transformations that occurred in the entire sample as you go from redshift 3 down to 2, down to 1, down to the nearby universe. So this is useful for science as well as just classification. Another thing that Mark did that we're finding very useful locally is he trained his deep learning code to mimic GalFit. So GalFit measures magnitude, Sersic indexes, sizes, and also axis ratios. And what this shows is that this is GalFit, this is the CNN, convolutional neural net, in other words, deep learning. And you see there's a one-to-one correspondence. There are some failures, but Mark says that the failures, the not perfect agreement, is about as good as GalFit run twice on the same sample. So the difference is that this analyzes 1,000 galaxy images per second, whereas GalFit can take many hours, and there's often some problematic ones. So in some ways, this is much better. This is another test. So here, we're plotting all the different images. So we generate 19 different images from 19 different directions for every simulated galaxy for the Vela set. So we do that by surrounding it with cameras, and some of the cameras are completely randomly located, others are located at fixed positions with respect to the galaxy. So there's face on, edge on, and then there's several cameras that are fixed at fixed positions, but sort of random positions, but kept fixed with respect to the coordinates within which the galaxy is simulated. So we have 19 different cameras. We have about 40 different time steps that we save for each one at least, from redshifts of 4 down to 1, and 19 different cameras. And then we generate images for all the roughly 15 wavebands that are accessible with the standard filters on Hubble, and about 20 different wavebands for James Webb Space Telescope. And so that's about 800,000 images have been generated. So this shows the 19 different images that are generated from different directions at each time step. And this is going from about redshift 3.5 down to redshift 1. And this is one of these plots from the Zolotov paper for the Vela simulations. So this was a compaction event. The gas density goes up. At this point, the stars become equal and then dominate gravitationally over the dark matter in the central part of the galaxy. This is on larger scales in the galaxy. This is the inner 1 kiloparsec. This is the 10 kiloparsecs. So at this compaction event, suddenly there's a big increase in the likelihood of there being a bulge, although that's the median. You see there's a big spread if you look at it from all these different directions. And then bulge goes down and bulge plus disk comes up. That becomes the more typical thing, because after compaction then, as you heard Avishai and many others describe, you typically get a rotating disk galaxy. And as Reinhard Genzel said this morning, that seems to be very typical to what we see. And then here, there's a final merger, and that then actually makes the bulge plus disk probability drop. So this is basically showing that by analyzing mock images, it is possible to disentangle what's going on, although you got to be careful, because depending on the orientation that you happen to catch the thing at, you might get misled. Still, if we look at many, many different images, maybe this will work pretty well. We're still working on all these things. So our very ambitious goal is to give deep learning mock images and mock spectra plus simulation metadata. The simulation metadata consisting of, did it have a recent major or minor merger? Was there a counter-rotating gas flow? Was there a big gas inflow, etc.? So that'll be the training set. And then we'll give images from other simulations to deep learning and see if deep learning can then tell us which of these things was likely happening. This is very different from the idea of trying to extract certain features like tidal tails as an indication of mergers. Just like that didn't work very well for classifying things in the artificial intelligence community, we're hoping that deep learning is going to be much better for classifying things. So in the best cases of signal to noise and resolution, this might help discriminate between different causes of compaction. As you've heard, all of these things can cause compaction. The images plus spectra could also help discriminate between shear caused by mergers versus rotation. So Greg Snyder and Raymond Simons, Raymond is here and talked earlier, have created a software pipeline to generate all these images and IFU data cubes from the Vela simulations, and it should work essentially with all modern hydro simulations. So this is not specifically for one particular kind of simulation. And Avishai's group and others have been, here at Santa Cruz, have been constructing this very big metadata. Incidentally, we plan to make all of this information publicly available together with the simulation outputs. So this is an example of very high resolution image. This is a James Webb type image of one galaxy from redshift 1.78 down to 1.44. This is a different galaxy from redshift 2.23 down to redshift 1.78. So you see how it's changing morphologically. There's obviously some big mergers happening here. This is an HST set of images, so not nearly as nice as the James Webb images. This is KMOS velocity maps and dispersion maps. You saw a bunch of these in Raymond's talk. And this is a kinematic rotational decomposition, again, much as Raymond described. These are just the sorts of images that we generate. So this is at redshift 4. We're going to follow the same galaxy from the same orientation. And That's redshift 4, redshift 3, redshift 2, redshift 1. And again, this was just one of the 19 cameras. And of course, that's just a few of the time steps to give you a sense of what's available. So this is the same video that Raymond showed. These are the young stars. This is one of the simulations. I think it's Vela 7 at redshift 1.7. This is what KMOS would see. And it looks, they would interpret it, I think, as a rotating galaxy. But this is what NIRSpec would see looking at the H-alpha. And here you see very clearly that there's much more going on. Yeah, there's a little rotating part there, but that's not the dominant effect. The dominant effect is a big merger. From a different orientation, again, that's what KMOS sees. This is what NIRSpec sees. So James Webb is scheduled to go up next October of next year. It looks like it may be on track, and it's going to be a wonderful source of data that's going to help us really figure out what's going on. Now, yet another thing that we're hoping to do is to improve the mixture of mostly photometric with a few spectroscopic redshifts. We're going to be getting millions of spectroscopic redshifts from DESI and Euclid and other sources, but we're going to have billions of photometric redshifts. So how can we make the best use of a mixture? So this is a paper that Nicholas Tejas, Aldo Rodriguez-Puebla, and I submitted, and we're still arguing with the referees, but presumably sometime soon this will be out. Anyway, what we did is we just took a simulation, Bolshoi-Planck, and we divided it into mostly photo-Zs, which are just the real redshifts, but spread with a Gaussian, and a few spec-Zs, which are the true Zs. And then we tried to recover the true Zs by a method that we called sort. And I don't have time to go into how it works, but this is what the photometric to true redshift distribution looks like, pretty awful. This is what the sort redshifts look like, not bad at all. And it allows you to recover pretty well the two-point correlation function on scales bigger than about 3 megaparsecs. If you just use the photo-Zs, you don't even recover it on 40 megaparsecs. So is this optimal? No, it's not optimal because we designed a particular scheme. Bryce Menard and his collaborators have a different scheme that works better for very large format, but neither are optimal. To get an optimal scheme, maybe deep learning can help us. So that's another one of our projects. Another project that we've been working on here, this is one that ex-Franchesca has been involved in. Franchesca classified by eye the initial sets of low-resolution spectra coming from Sloan. But Sloan recently dumped 240,000 additional spectra. And it becomes, I think, tedious for humans to go through that scale of spectra. So David Park, a grad student here working with Dr. Xiaofeng Dong, Franchesca, and Zhang Kai, invented a method that uses a sliding window and can easily detect even double damped Lyman alpha systems. And I think they're just about ready to submit their paper and publish their entire catalog. So this will be an increase of a factor of 4 in the total available number of damped Lyman alpha systems. So again, another application. Now, the scale of big data in astronomy has been growing exponentially and will continue to do so. So the Sloan Digital Sky Survey was about 120 terabytes of processed data, starting from 2.5 terapixels of images. The Mikulski Archive for Space Telescopes, MAST, in 2013 had about 25 terabytes per year ingest and 100 terabytes per year retrieval rate. And it's been about 5 years since the number of papers based on HST data, based on archival data, exceeded the number based on new data. So the archival data is way ahead now. So MAST is 100 terabytes a year. The LSST, the camera's being finished, and Steve Ritz, who gave the opening welcome last Monday, is in charge of building the camera, the 3.2 gigapixel camera. It will take an image of the entire southern sky roughly every 2 nights. All the telescopes in the world discover a few thousand supernovas per year. LSST will discover 1 million transients every night that'll include about 10,000 supernovas, new supernovas every night. It's 15 terabytes of data per night, and you can't get behind on processing that. So, and then the square kilometer array is going to be generating an exabyte of data a year starting around 2024. So these are fairly large scale data supplies. This is the total amount of an exabyte per year is the internet traffic today. So we're going to need a lot of help analyzing this kind of data, and I think we're going to need to use machines that can learn to do it. So this is just a list of the things I just told you about. Thanks very much. Oh, of course. If we find that, see, I don't expect it's going to work all the time. There may be inclinations edge on where it doesn't work very well, or low signal to noise, or poor resolution, too high a redshift. So what we're going to find out is where we can reasonably expect it to work, and then those are the cases where we have a chance to believe something reasonable will come out. Similar enough, yeah. Well, we've already checked. Yeah, we've already checked some things. So, for example, Sandro Tikela, in the paper he published, one of the two papers that he led last year, compared the radial distribution of stellar surface density in galaxies, real galaxies versus the Vela simulations, and in 3 different mass bins at an average redshift of about 2, over 4 orders of magnitude in surface brightness, the agreement was really superb. So, you know, the simulations aren't perfect, but some of these simulations are doing really quite well. If the simulations weren't doing pretty well at things like that, matching the right size, evolution, and so forth, yeah, sure, you couldn't expect this to work. But as the simulations get better, it should work better and better. Yeah, okay. At those high redshifts, who knows? But JWST won't just be used to look at high redshifts. You know, it's a 6.5 meter telescope with much better infrared capability. And so we're going to want to use it to also look at redshifts of 1 and 2 and 3, where it's going to give us a lot more information than we've had available before, which is what I tried to show you, and also what Raymond showed. Yeah. I don't know of anyone here who's thinking of doing that, but sure. I mean, the general experience with these convolutional neural nets has been that they're unbelievably good. And so probably, since they seem to work for all kinds of things, with enough work, you can get them to work for other things. So maybe interpreting all spectra. Our general experience has been, I mean, we've made lots of codes open source, and we probably will do the same once we've got things worked out. Also, it said this in the slides, I didn't mention it, but Google has been helping us a lot. They even gave us some money. And a bunch of Google, of the machine learning experts have come here. We've gone up there. We have the advantage of being only 45 minutes away. And they also are very much in favor of publishing. So I expect that we'll want to work with the community as usual and make things publicly available.
I think we have to move on. So thank you, Joe.